All right. To start, I have an announcement to make. This affects everybody. It's kind of a big deal. Ms. Kulik made a mistake. So when he set up the grade book for the course, I transposed two numbers. So according to the syllabus, the test scores are supposed to be 50% and the semester exam is 15%. Somehow those two numbers got transposed. I fixed that yesterday morning, so if you saw your grade change for reasons you didn't understand, that's probably all that happened, is that calculation was readjusted. That's all. So again, I just typed something in wrong and transposed two numbers and fixed that yesterday morning, so I think very little would have changed in a class like this unless you had like a missing test that still hasn't been taken yet or something, in which case you probably had a big chunk taken out of your score or something, but figured I needed to say that. That being said, Anthony, when you get a chance, the quiz needs to go in the folder. Today we're starting chapter 10. So in chapter 9 we talked about what a derivative is and how to find the derivative of a function, whether it's in general or at a point. In chapter 10 we're going to look at applications of a derivative, and we've kind of hinted at, no, that's not for you guys. We kind of hinted at some of those applications already in chapter 9 as I was discussing, but we're gonna look at those applications here specifically in chapter 10. So this is, thank you. We'll be using all the tools we developed in chapter 9. We're just gonna be applying them to specific problems now in chapter 10. So the first thing we're going to talk about is locating extrema. So if you remember back to your algebra courses, there are two types of extrema. There's maxima and minima. A maximum occurs when a graph changes from increasing to decreasing. So if we put it in terms of calculus, the graph is increasing when its derivative is greater than 0, and it's decreasing when its derivative is less than 0. So we can adjust our definition of a maximum as where the derivative changes from positive to negative. And the minimum then would be the reverse, right? That's going to be where the derivative, or where the graph changes from decreasing to increasing, or where the derivative changes from negative to positive. Everybody okay with that idea? So that idea is just going to be called the first derivative test. So locate the places where the derivative is either 0 or undefined, as those are the two ways that the graph could hop from a positive value to a negative, or from a negative to a positive. And then we'll just do some test values and kind of make a sign diagram like we did to solve an inequality in pre-calculus. The other option is we can do a second derivative test. So I take those places where the first derivative was equal to 0, we call those critical points, and then we plug them into the second derivative, and if the graph is concave up at that situation, then that point would correspond to a minimum, right? Concave up looks like a U. And we can tell whether a graph is concave up or down from its second derivative just based on whether it's positive or negative. Positive is up, negative is down. And then we can do the same thing for if the second derivative is negative, that tells us it's a maximum because it's concave down, right? Looks like a hill. Is everybody okay? So, point of order, the first and second derivative tests do the same thing. They're going to tell us where the extrema are on our graph. So, does it matter which one we choose to use? No, they both do the same thing, right? 99% of cases you'll have enough information to do either one. There are rare exceptions where one of them may be more practical to use than the other. But I don't know that I've seen in this class any of those situations kind of come. Okay? Now, these first and second derivative tests are only going to give us the local maximum or minimum. What's the difference between local and absolute? So a local maximum would be like the highest point in an open interval, like some neighborhood. An absolute maximum or minimum is the highest point across the entire graph, or the highest point over some domain, some closed interval on the graph. You know, some restricted domain. So if I want to check for an absolute maximum or minimum, one, I have to have a closed interval. Okay? And then all I do is I perform my first and second derivative test, find all the local maxima or minima, and then I check the values of those local maxima and minima and the endpoints of the function. The highest or the biggest y value I get is the absolute maximum, and the smallest y value I get is the absolute minimum. Because if it's on a closed interval, you know, I could have something like this. Right, where the extrema, the local mins and max, may not be the absolute min and max. I also have to check the endpoints, right? If it's on a closed interval, I have a hard endpoint, which could be the highest or lowest point in the graph, so I have to check those also. But that's the only additional concern if I have a closed interval. Is everybody ready to do some practice? So from here on out, all we're going to be doing is practicing these first and second derivative tests and this procedure for finding an absolute maximum or minimum. We're going to do them both ways so you get a feel for like the first and second derivative test, how they work. Do you ever have to do it both ways? No. One or the other is all you need. All right. So, here we say, find the coordinates of the local maximum or minimum of a function, f of x equals 2x squared minus 12x plus 15, and identify it as a maximum or minimum. So, the first step is going to be taking the derivative of f. So how do I take what is the derivative of 2x squared minus 12x plus 15? You just turned in a take-home quiz on this topic. You should be able to do this quickly in your head.
4x minus 12.
4x minus 12. Any questions as how we did that? Okay. Again, if you need to show more work than that on your paper, that's totally fine. But at this point, We've done practice on this, you've done multiple homework assignments doing this, you did the take-home quiz doing this. This is something we should be comfortable enough that we can start rat-tatting these guys out just in our head. I understand if it's something more complicated, but if it's a polynomial with integer coefficients, like, guys, we can handle this. All right. What I do now is I look for the critical points. So I need to find out where the derivative is 0 or where it's undefined. Those are the only possible places where the graph can jump from being below the x-axis to being above the x-axis or vice versa. Let's start with the undefined part. So are there any values for x that when I plug it into 4x minus 12, would it make the function undefined?
No.
No, very good. Why?
Because all those numbers, something can go in all of them.
Okay, what type of function is 4x minus 12? Okay, more generally than that, it's a polynomial, right? The domain for any polynomial is all real numbers. Is there anything that's undefined then? No. So whenever my derivative is a polynomial, I know the answer to this piece is just, there's no x's over there. Now, in this class, I kind of doubt that there's ever going to be a situation where you pick up a value. I can think of one specific case where you have enough tools to I can give you a derivative that picks up a value there, but I don't think it'll come up in the homework or the test, the IB exam or anything. So let's focus on this other one. If I set 4x minus 12 equal to 0, I get a solution of 3. It's my only critical value. Everybody good? Okay. So I'll do a first derivative test, and then I'll do a second derivative test afterwards, just to kind of give you a feel for what are we doing, what's the difference. Okay with that? So my first derivative test, I'm going to make a sign diagram. The x values on my number line are going to just be the critical points that I found in the previous steps. In that case, there's just the number 3. I'll pick a value that's from either side of those critical points so that the whole number line is sectioned off, and I pick a value from either section. Does it matter the value from the section I pick? No, just keep it simple, right? All right. What I do then is I'm going to take those test values and plug them into the first derivative. Now, I could compute the actual number, but I don't really care about the number. What I care about is if the derivative is positive or negative. So that's really all I'm going to worry about. So if I plug 2 into the derivative, 2 times 4 minus 12 is negative, right? 8 minus 12, that's negative. If I plug 4 into the derivative, 4 times 4 minus 12 is positive. So since this graph has gone from decreasing, negative derivative, and then changes to increasing, a positive derivative, what type of extrema do I have? It's a minimum, right? Now, careful on the question because it asks us for the coordinates. So we know the x-coordinate of a minimum is at 3. We also need the y-coordinate now. How do I get the y-coordinate? I use the original, right? I just plug 3 into this. So that's 18 minus 36 that's negative 18, plus 15, that's negative 3. So I have a local minimum at 3 comma negative 3. Yes? Sure. Does that feel okay? So to accomplish the same thing, I could do a second derivative test. You never have to do both. This is just the other option. To do the second derivative test, I start by finding the second derivative. So it's the derivative of 4x minus 12. 4. Okay. I then take my critical values and plug them in to the second derivative. What's the second derivative of 3 have to equal? Just 4, right? The second derivative is a constant function. Doesn't matter the x you plug in, 4 is what comes out.
Repeat 13.
It's not 13, that's of 3. That's function notation, right? Since this is greater than 0, the second derivative test tells me that that means it's a minimum. And then I calculate the y value doing the same thing. I'm not going to repeat the work there. So it means we have a local minimum at 3 comma negative 3. Does everybody feel okay? Now, if the derivative is easy to compute, I think the second derivative test is a little bit quicker because you only have to plug in the critical points into the second derivative. You don't have to do a bunch of test values. But it's a matter of preference. Either is fine. And almost I can't, going through and looking at the homework, I don't know that there was any situation which you couldn't do either one. We feel okay so far? Let's do another example. Here we're asked to find the x coordinates, so we don't care about the y's, we just want the x's of all the local maximum and minima for the function and identify them as either a maximum or minimum. Right? Ostensibly the same problem as before. We should start by finding the first derivative. What's the derivative of x cubed minus 4x squared minus 3x plus 12?
3x squared minus 8x minus 3.
Good. Anybody with questions on how we did that? Okay. Then we take that first derivative. We set it equal to 0 or undefined. Let's start with the undefined. What are the values for x that makes the derivative undefined?
None.
None. Good. Why?
Is a polynomial.
Because the first derivative is a polynomial. Will that be what happens every single time? No, but in this class, probably. In general, the answer is no, but in this class, probably. All right. How do I solve then 3x squared minus 8x minus 3 equal to 0?
Quadratic formula.
Could do the quadratic formula. What are the other methods that we could use in addition to the quadratic formula?
Oh, you can.
So you could graph it on your calculator and find the x-intercepts, yep. And the third option would be factoring, yep. So those would be the 3 primary ways that I would go about trying to solve this. If I'm on the IB exam, where rounded answers are perfectly fine, I would probably just graph it and find the x-intercepts. Here I'm going to just do the quadratic formula just because it's a little more rigorous and I like rigor. All right. So negative b plus or minus square root b squared minus 4ac all over 2 times a. If you don't have that memorized, God help you. It's been a while. 64 plus 36 is 100. The square root of 100 is 10. 8 plus 10 over 6 is going to be 9 over 3. 18 over 6 is 3, sorry. And then 8 minus 10 over 6 is negative 1/3. Everybody's okay? Just arithmeticing, right? Ooh. So now I'm going to draw my sine now it's time for the first derivative test. Or the second, right? We'll do both of them again just to give you a feel. Everybody okay with the test values I picked? Notice I needed 3 of them. Okay. Come on. All right, so if I plug negative 1 in, I get 3 plus 8 minus 3, that's positive. If I plug 0 in, I get 0, 0 minus 3, so that's negative. And if I plug 4 in, I'll get 48 minus 32 minus 3, that's positive. Again, notice that I didn't bother finding the full number. Like, you're welcome, I mean, you have your calculator, type it in, you know, like there's no reason not to do that. Get the full number, but for this purpose of me doing this at the board, I don't really care what the number is, I just care about what the sign is. All right, so the negative 1/3 goes from increasing to decreasing. What's that mean it is? Maximum. Again, if you draw yourself like a little picture, increasing to decreasing. 3 goes from decreasing to increasing. What's that mean?
No.
Minimum. So there's my second derivative test completed. Notice I didn't have to plug these values for x back into the function because it did not ask for the coordinate. It just asked for the x coordinate, didn't ask for a coordinate pair. If I want the second derivative test, I need to take the second derivative. What's the derivative of 3x squared minus 8x minus 3?
6x minus 8.
6x minus 8 is correct. I then plug in my critical values in. So if I plug negative 1/3 into 6x, I get negative 2, and then minus 8 is negative 10. That's less than 0, so that's a maximum. If I plug 3 in, that's 18 minus 8, so that's positive 10. So that's a minimum. So we're done. We have a local max at x equals negative 1/3, and a local minimum at x equals 3. Again, you're accomplishing the same thing. You can use either method. It doesn't matter in most cases. It's just a question of preference, which one you prefer, right? So far, so good? All right. Next one, it says h of t is equal to 4x cubed plus 3x 4t cubed plus 3t squared minus 6t with the domain from negative 3 halves less than or equal to t less than or equal to 2. It says find the coordinates of all the local extrema, classify them as minimums or maximums, same as we've been doing. And then part B says write down the coordinates of the absolute maximum and absolute minimum. So we can ask this question because we have a closed interval, right? If I don't have the closed interval, it doesn't make sense to ask that absolute question. Not without some more theorems or whatnot. Everybody okay? So part A, same as we've been doing. So we'll start by finding the derivative of h of t, which is, what's the derivative of 4t cubed minus 3t squared minus 6t?
12t squared plus 6t minus 6.
Good. And then just like before, we'll set this equal to 0 and undefined. What values for t make this undefined? None. Why? Because it's a polynomial, right? Everybody's okay? Very nice. All right. So setting it equal to 0. I noticed something right away that would make the solving a little bit easier. Does anybody else see it? Yeah, all the coefficients are divisible by 6. So if I divide both sides, or you could think about it as like factoring a 6 out, but since it's an equation, I can just divide it to both sides, and then the 6 is just out of there. I'll factor this, even though the leading coefficient is 2, this is about as easy of a leading coefficient is not 1 problem as I can, because there's only 2 choices that multiply to get me negative 1. Just 1 and negative 1. So it's a question of like, which spot does the negative 1 go and which spot does the positive 1 go? So there's just like a 50-50. I'm just going to kind of do it by inspection. Since that middle value is positive 1, I know that the 2 has to be attached to the positive 1, and the 1 has to be attached to the negative 1, so that when we do our FOIL, we get that. Everybody's okay? So t equals 1/2. And t equals negative 1. Now, I should take one moment here and pause now that I've found these critical values and make sure they're both on the interval that we've been stated at the beginning, which they are. Now, I would find it unlikely that when you solve to find your critical values, you find critical values that aren't on the closed interval that you've been provided. But it's not impossible, like it's just being thorough to check to make sure, okay, I care about both these numbers because they're both on the interval that I'm concerned with. So if I do a first derivative test, then pick some values for t. Now, I do have to be a little bit careful here when I do this because the values for t that I pick have to be on that closed interval. So as much as I'd like to avoid having a fraction here, I'm going to pick negative 3/2 because that's the bottom of my closed interval. I know, it's unfortunate, but because I did the factoring, it's not too bad. When I plug negative 3/2 into this, I'm going to get a negative here and a negative there. So that's going to be positive. When I plug 0 in, I get a negative times a positive. It's negative. When I plug a 1 in, that's positive times a positive. That's positive. So if I go from increasing to decreasing, that is a maximum. And then from decreasing to increasing, that is a minimum. Now it asks for the coordinates here, so I have to then find the y coordinates. So I go back to my original guy here, 4, 3, negative 6. Oops. So that's negative 4, plus 3 is negative 1, plus 6, so that's 5, I think. All right, let's see here. That's going to be, I'm going to have to write a little bit of work. 1/2 plus 3/4 minus 3. So that's going to be negative 1.75. Everybody's okay there? If I want to do this as a second derivative test, I'll need that second derivative. Oops, these are h's and t's though, huh? Okay, so the derivative of 12t squared plus 6t minus 6 is? Thank you. And then we just plug in our guys. We find the same conclusion. We do the same thing and plug in the values. And I guess either way we conclude we have a local max at -1, 5 and a local minimum at 1/2, -1.75. I'll write it there, kind of as a joint. So that's part A. Part B then says to find the absolute maximums or maximum or minimum. So in addition to these, I also have to check the endpoints. So the endpoints of that closed interval were -3/2 and 2. So I'm just plugging these in just like I did before. I'm gonna hope that I can mental map this. It's awful early for this stuff. I'm going to start with this one because I know I can do this one. That's 32 plus 12, so that's 44. Minus 12 is back to 32. And this one, let's see, that's going to be 9/2. Oops, no, -27/2 plus 27/4 minus 9. So that's going to be -54/4 plus 27/4 minus 36/4. So that's -27/4, 53/4. No, 63/4. I think, right? 27 and 36 is 63? Yeah. Okay. So if I look at this, the, assuming I didn't make any arithmetic mistakes here. Yes. I think I got it. All right. So the biggest y coordinate, I'm looking at all the y's. Which one is the biggest? And then I look at all the y coordinates, which one is the smallest? That one, right? That's it. Notice that part A helped us out in finding the coordinates. I need those y coordinates for the local mins and maxes to compare with the endpoints, because I need to find the highest y value or the smallest y value among the three. Or four, sorry. Everybody feel okay? This is like the same question. I'm going to skip that. I want to do this one because this is like, you kind of have to do it on your calculator. Because notice the terrible function that we have here. It says a fruit distributor has noticed the weekly change in the price of apples can be modeled by the function PC equals yada yada yada. Notice it's got a sine function in there. There's no way you're taking the derivative of this by hand. Where PC is the change in the price of a kilograms of apples, and X is the number of weeks since the start of the year. So this guy is like, the unit here is like some dollars per week, right? What does this sound like? That sounds like the first derivative, doesn't it? Because it's written as a rate. Its unit is a rate. Okay, the fruit distributor would like to plan a sale when the price of apples will be at a minimum. What week should the sale be? So what I'm going to do is I'm just going to graph this on my calculator and look for the x-intercepts and look at where the graph changes from negative to positive. Oh, that's y equals. Now, I just moved you so you'd be, so I could see this thing. And then I need negative 13 divided by 52 times sine of 90 divided by 13 times x minus 5. Now, what would be an appropriate window to use on this? It says x is the weeks, number of weeks from the start of the year.
Zero to 52.
0 to 52 sounds excellent. Why 52? That's such a strange number, Marin.
Because there's 52 weeks in the year.
Oh, yeah. Duh, right? Now, the y values are going to be like the price, the dollars. Anybody have any idea what a kilogram of apples ought to cost?
A kilogram of apples is probably 50 cents.
You are crazy. You need to go grocery, except put in a grocery store. A pound of apples is like $3 or $4, right? A kilogram is 2.2 pounds. So I would guess that like -5 to 5 would probably be appropriate. Here, I would suspect they'll be quite a bit lower than that, but I feel like that's probably a fair guesstimate. Notice how real life kind of informed this. Oh my God. Do they mean this to be in degrees? Because that's what they meant then. They meant your calculator mode to be in degree. I think in this class it's always assumed that your calculator is in degree mode. That's an important point.
Sure.
So it looks like I have 2 places where, or maybe 3 places where the graph crosses the x-axis. You guys see that? I'm going to change my y scale to make it a little bit easier to see now. So I can probably go from like -0.5 to +0.5 and be good there. That gives me a little bit better picture. I see 2 places, right? So this one, we're going from increasing to decreasing. That's going to be the maximum price change in apples, or price of apples. Here, we are going from decreasing, because it's negative, to increasing. That's going to be the minimum I'm interested in this week. Is everybody okay? So second trace, 0 command, left bound, right bound, guess, week 31. Sales decrease when the price of apples reaches its maximum. In what week will the price of apples be highest? Oh, well, we identified that a second ago. That was this spot, right? Second trace, 0 command. I'm gonna press this 100 times here. Oh, the scale's so bad. There we go. Enter. That'll do. Enter, enter. Week 5. Is everybody okay with what we did here? Notice the hardest part about this was recognizing that what they gave you was the first derivative of price. You recognize that? All you really had to do was graph it and look at the picture. What do you guys think? It's okay? I think it's relatively straightforward. For your guys' assignment, 10.1, I forget the page numbers. I know it's 1 to 15. There you go.
Yeah.
How's that feel, guys?
Great.
Great.